personal data. So it's a lot. It's really a lot of IDs that have been stolen or leaked. Interestingly, the prevalence of data breaches maps quite well with internet utilization. So on the top you have the prevalence of data breaches. So this is a graph I took directly from the website of the Open Security Foundation, and below you have the number of users of internet worldwide according to the International Telecommunication Union. You see there's a quite good mapping. That said, data breaches do not necessarily relate to internet users. I mean, a retailer holding the credit card numbers of like Walmart, holding the credit card numbers of customers can also be suffer kind of a data breach. But I think this map shows that there is kind of a relationship between connectivity of people, telecommunication systems, and the prevalence of data breaches. Also, just to show some statistics, you can see the evolution of with interquartile range, interquartile range of the lag of between like an incident has occurred and it has been reported in the database. So this adds some kind of robustness, shows that in fact this lag has heavily decreased over time. So it's not that bad. Just think about like the scale in ordinate is log, so it means that the decrease is quite huge. We might also be interested to see the lag as a function of the size of the event, but this is fairly flat. So it means that whatever the size of the event, it won't really influence the reporting. Also, we want to know about the completion of the catalog. Think about like here we are right on a fault, a seismic fault. And to detect earthquakes, we need some sensors that are just scattered all over the country, and these sensors have a capability to record some earthquakes of some kind of magnitude. And today we are in the same situation. It will be extremely hard to record some events or some incidents that just concern 1 or 2 or 3 persons. It's way more easy to record events that are involving 70 or 100 million users. And so the completion of the catalog is an important issue in terms of robustness. What we see is that it has decreased heavily in the last years. So it means that like the curators of the database are just capable of getting access to data that concern smaller events. So what can we do with this database? In fact, we can just calibrate a distribution, and this is what we get. So if you look at the distribution, it's so here is a rank ordering, so it's equivalent to a complementary cumulative distribution. And if you look at that in a double linear scale, what you will see is very striking. You see that 10 extreme events account for 35% of the amount of total loss of personal ID. So it means that like the larger event, for instance, is 150 million IDs that have been stolen at once. So over the 2 billion. So it means that 700 million personal ID have been stolen in 10 events. And what you see here is a multitude of very small events. Of course, they count. They are not like negligible, but they are way smaller. So what we can see immediately is that the distribution is heavily skewed. And so if you look at the distribution in a double log scale, what you see is roughly a straight line. Okay, we'll just talk about the upper and lower cutoff in a second. But what we can see is that over many decades you have a straight line. And this qualifies a power law, and the exponent of this power law is smaller than 1. And Mandelbrot called this kind of distribution wild distribution. Why are they wild? Because of their intrinsic nature. There is no variance and no mean defined. So it means that the more time passes, the larger the mean, the larger the variance. And this is an issue because it makes just the distribution and the process uncontrollable, just continues to grow. And in fact, like this no variance, no mean, the fact that the variance and the mean just diverge is due to the extreme events. So you might always have one point that is just way bigger than the ones that occurred before. Think about like earthquakes. I mean, that's really the best comparison. Think about like in Japan. Nobody really seriously expected magnitude 9 earthquake in Japan, and still it occurred, triggered a tsunami that just destroyed a nuclear plant. That's kind of things that people say, oh yeah, that's sufficiently rare that we are not just taking care of. But in fact, we care because these are these extreme events that really make the most damage. Just to show a few other examples, so earthquakes, same distribution in log-log, you have a straight line. Of course, it's much more straight because more earthquakes have been recorded, so we can have more robustness on the statistics. Work we have done recently with co-authors is the distribution of nuclear risks. Same thing, distribution, power law distribution with an exponent which is small, 0.7, also a wide distribution. So we should not be surprised if one day there's a new nuclear meltdown that just is 10 times bigger than Fukushima. So that's something we should get prepared. Also, another extreme risk in society is the risk of war, the size of wars. And interestingly, there are like two distributions. One for the wars before nation war, before Napoleon, and the wars after Napoleon. So after Napoleon, it went much worse than before. Also due to the invention of way more efficient weapons. So, but let's go back to the power law distribution, and we can learn more than just that it's a power law. What can we see? If we look at first, we want to know whether this distribution is robust. So, is it stable over time? Does it tend to change, or is it kind of the same? So, we just studied the same distribution like since 2005, and each year we just looked at the distribution with the new events updated. And what we see is that same thing, like the allure, the shape of the distribution is the same, but the exponent went from 0.7 in 2005 to 0.6. So yes, that's not that different. That's true. It's kind of stable, but still tends to be a bit more extreme. Also, we have a cutoff, a lower cutoff. So the power law distribution is only defined beyond some threshold, and we see that this threshold tends to reduce. So it means that we see like the increasing completion of the catalog. That's the lower cutoff. So we are happy to see that because we know now that the database is just recording like more data or like small events. And what we see here is an upper cutoff. So we should have, let's say that if these statistics will be very robust with a power law distribution, we should expect to have like events at 1 exponent 9. And we don't have them. It seems that there is a kind of a size limit around like 150 million. So we don't know. That's really the technical part we are still investigating. We want to know whether this kind of apparent cutoff is embedded in the statistics. So we should just expect that there's some deviation. Just think about like that there are not so many points here. So it's a very low sample statistics, not really, not very robust. So we don't know yet. We are just investigating several scenarios. And but that's an interesting question that I will raise again in the discussion. Now what we want to know is all these things might evolve in the future. And from the distribution we can make one prediction. The prediction is that the number of the V being the cumulative number of loss, of ID loss, should grow as 1 over mu as a function of as n and the number of events as exponent 1 over mu being the exponent of the distribution. So according to our calibrated slope, our mu exponent, we should have n exponent 1.7. But n assumes that, or if you want to translate that in t, you want to make a change of variable. You want to say, what is the and then you want to know what is the function of n as a function of t. And so what we observe from this graph, so again log scale, so we have a scaling, so it's kind of it's not exponential, but it's kind of the same as an exponential, just grows extremely fast. You will see a graph after with a slope of 3.56. So in fact the number of observation grows as t exponent 3.56. Then if you combine the two first equations, you get the third one, which says that the prediction tells us that we have like a growth of the number of events of loss of t exponent 6.1. But what we observe here, so we can measure this prediction, we see that the slope is 3.75. So what we see is not that worse, is not as bad as what we would expect from the model. And there are two explanations for that. We don't know yet. First, there's no explanation. We don't know. We are just investigating. But one is remember, the completion of the catalog. So there are more and more small events that are sampled, and these small events contribute very little to the increase of cumulative loss. Think about like the very big events. But if you just add small events, they just contribute a lot in terms of cumulative events, but very little in cumulative loss. And also, the upper cutoff might also play a role. Think about like this distribution being cut here. If we would have some events that just go in this direction in straight line, we should have like more events. So on both sides, the contribution of this lower cutoff and the upper cutoff just favor kind of having a smaller slope in terms of cumulative loss, which is a good news. We want to have as little IDs stolen or lost as possible. Just to show you this, what is the kind of to get an impression of what is this n exponent 1 over nu is. If you look at the top 10 events, and you want to see like when the top 10 events occur, you see that there is one in 2013, there is one in 2012, and there are 5 in 2011. So out of 10 events, 7 have occurred in the last 2 years, over 12 years of sampling. So that's the idea that the more time passes, the more we will have extreme events, and the more these events are sampled. So this is frightening. I mean, if I come back here in 2016, we'll find out probably that the 10 worst events, 60% of them or 70% of them are probably have not occurred yet, sort of, or will occur in this period. And since the distribution is quite stable, and as you could see, the dynamics of cumulative events and loss is a very nice straight line, a very nice scaling. We can make some forecasts, and even though it's not that bad as the prediction says, it's frightening. So what we can say is that, or expect, unless there's a major change of regime, we never know, is that by 2018 we'll have 70,000 events, accounting for 4.2 billion of ID loss, which is more than the number of internet users by 2020. And in 2020 we'll have a cumulative loss of 7.1 billion, which is more than the actual population today, not in 2005. So of course, this is, well, we can also think about that. This is probably also a lower bound because, of course, our data set is not complete. Only records some events, and probably it's way more than that. So the big question is like, okay, how is it possible that we have more IDs stolen than the population, the world population? This is very stupid. It's not, in fact. Like, people have multiple IDs, or IDs can be stolen multiple times. So let's say credit card numbers can be stolen multiple times. Also, an important point is that why is it that we are not suffering that? Usually, I take a poll of the room asking how many people have suffered an identity theft. Some say that it occurred, but usually we don't suffer as much as these figures show. And the idea is that an identity loss doesn't say identity theft, doesn't imply identity theft. So it means that many data might be somewhere in the wild, might be leaked or in some servers underground, under the radar, but they are not used, or they are just useless. Think about like a credit card number. There's a purchase date to the credit card number. After some years, it just gets invalid, and the credit card number is changed, and that's it. So it's useless. So there's a kind of pollution. So there are like some IDs that are lost, but they are not useful for theft. There's an obvious conclusion, or something we can discuss, is like, of course we have like very big events, but if you want like to steal 100 million IDs in one event, you're better off finding databases that are at least as big as that. And so the distribution says implicitly that, in fact, big data is very much exposed to identity theft. And so the big question is there how much? I mean, how can we say something about the probability to get an extreme event in the database conditioned on the size of the database? So this is something we don't know about yet, and it's too bad. I would love to make a statistic that says, okay, given the size of your database in terms of number of users, I can tell you what is the probability that you will suffer the loss of 10%, 20%, 50%, or 100% of your database in terms of being lost or stolen. And also, what about super big data? Let's say bigger than 500 million users. Facebook, Google, Yahoo, Microsoft. So our distribution says, oh, there's maybe a size limit. We cannot sample further than 150 million. So an open question is, okay, if we buy that there is a size limit, why is it that? Is there some technical limitation? Is it getting too complicated or too costly or too long to transfer hundreds of millions of data? I don't know. That's an open question. As I told you, this distribution also tells us about like really at the coarse grain level, not at the security level, but at the coarse grain level, might just tell us more about like what is the underlying mechanism of fragility, of security fragility that might explain this distribution and these dynamics. We don't know. We have some ideas. We're just getting inspired by earthquakes again to try to devise new theory to explain why we are just observing this incredible explosion of events and of loss. So what are the probable causes of this, what we are observing now, is concentration of data by companies and governments. So I said, well, we are not concerned with the National Security Agency because we are not concerned with the scandal of the National Security Agency aspiring all the data. But in a second order, we are concerned because these guys, they are just concentrating huge amount of data on people, and no one can guarantee they will never leak this data. And they are great guys, but they might not be just great enough to secure all their data. So I'm concerned with that. I'm a bit less concerned with them aspiring the data, but that's Yeah, that's the issue. I mean, can they just retain it in a secure way? Open question for me. Especially when you see what happened to the Department of State with these telegrams that were leaked on WikiLeaks. I think also it's very important, even though I won't just go more on that, there are like huge economic and political incentives to steal, exploit, conceal, or release personal data. Just exploit, or steal and exploit. Think about Google. Think about the power of Google using our data, my data, your data. I mean, any other competitor might want to have the same data or similar data. They won't be happy to steal some data from Google or from Amazon or to steal data from you just to be able to deliver the same advertisement as Google. So Google is just making a competitive advantage on our data, on the concentration on our data. I mean, it's very natural that some other entities might be interested to do the same thing. I think another cause, but still we cannot really explain it well, is the complexity of information systems. And I don't want really to enter this debate because we have very little evidence about whatever relating identity thefts or data breaches and the complexity of information systems. But I deeply believe that there is a root somewhere there. So the talk is entitled Statistics of Data Breaches and Privacy Erosion. And so I think privacy erosions deserve some kind of explanation. And I think that's the slide, or that's the thing I'm the most concerned with. The thing is that, as we have seen, like the amount of data, personal data stolen will be soon more than the entire world population. And these are consequences. First, some IDs can be hardly revoked. Okay, credit card numbers, that's okay. We can revoke it. You can just call your bank, say, I had this credit card stolen or credit card number stolen. Please just cancel this personal ID. But your name, much more difficult to change. Security social number, as far as I know, it's not possible to change. Of course, it's for administrative reasons. We could just make it be revocable. The thing about like fingerprint, now we have like this new iPhone. Oh, fortunately I don't have the new iPhone 5S, but fingerprint, DNA. With John, we are working on brainwaves. Just think about like your brainwave in the future being recorded and somewhere in the cloud and hosted by a data holder. Mobility patterns, something that you cannot change. You live in Berkeley or live in Oakland and come to Berkeley every day. You might have to change completely your. And this information is very interesting for people who want to impersonate you. But changing this pattern is extremely hard. You don't want to move, or it might just come at a huge cost for you. And another point is that, well, you might say, oh yeah, in fact there are like these events and data is stolen and leaked and maybe it goes back on the black market, and then there will be a market of identities, and it's not maybe, in fact it's quite sure. And this data is scattered, nobody cares. No, we care, because data can be reaggregated. So you lose some piece of information somewhere there, you release another piece of information somewhere on Facebook, and all these data, like at the atomic level, have little or no value, but together have the possibility really to impersonate you. And Alessandro Acquisti made a very nice demonstration. Didn't have even to go to the black market on data, stolen data. I went on the web and just pulled some kind of different data sets and could just reconstruct the identity of people. So this is really scary. Of course, that was a proof of concept. It didn't go far, could just recognize people, but just imagine in the future that we can just get access to better or more precise information. The capacity to impersonate people will be increased. And this is an issue. I call that privacy erosion because we should think about like a cliff. And this is a picture from Pacifica, so not far from here, of a cliff that is constantly attacked, by waves. So some amount of energy is provided to the cliff, and at some point the cliff just will collapse with landslides. And some landslides, the most of them are a move of a very little sand piles or of piece of rocks, but some are huge. And this is really the situation we are. But not only that's the situation, but in the case of cyber risk, the frequency of waves is just increasing with time, and increasing quite fast. So just think about these guys living there, and their property just suddenly just falling down in the ocean. Your data, your personal data, are this building on top of the cliff. So what are the consequences? For cyber insurance, it's quite clear. On the one hand, on one side, you have the data holders, so the guys having your data and aggregating the data. They face catastrophe risk. They face like risk they probably cannot afford. They can afford it at the moment because there's no regulation to force them reimbursed at the exact price what people suffer or might suffer in the future. And this is, so I'm not an actual guy, so I want to work with insurance companies, and I'm working with insurance companies to try to understand how we can just design insurance premium in order to better cover these people. And the very clear, so to insure like data holders, the very clear thing is that it will involve reinsurance and also states. So the risk is so extreme that insurance will not be sufficient. We'll need like some kind of secondary or third order coverage of the risk. And on the other side, we can think about individuals. In fact, we can also think about individuals being assured. And we are thinking with John of like, can we calculate the increasing probability of impersonation based on the leakage of your data? And that's kind of a life or a virtual life of health insurance. But we are just at the concept, so we don't know. Policy issues. And that's very clear that we have to tackle large extreme events quickly. And I think that's something governments have not solved about is the question of emergency response. It's quite clear that once like a big event or an extreme event has been discovered, all should be done to try to recover this data before it just goes in the wild. And as far as I know, there's no agency for doing that. Then there are more long-term problems. The problem of authentication. The more personal data gets leaked or gets out of control, the more additional data, personal data will be required for authentication, like more credentials, sort of. So we have a positive feedback loop. So the more we will allow like data getting kind of leaked, the more we will, data holders or websites will just ask you for more credentials. It has already started. When the internet was created, we just would enter a login and a password, and now you have to provide your birth date, the name of your dog, the name of your cat, all that things. I mean, so more and more data is required to get authenticated. But this data is ultimately goes also in the database. That might be leaked in the end. So of course, that's a concept. We should just try to measure how much this feedback loop is really powerful and makes a point. Then there's also an issue is that the market of lost IDs or stolen ID might be reduced. We'll just commoditized. The more data is leaked, the more the price will fall. And we should expect that more data will be stolen as this result. I mean, people who want to steal or use data, they might want to, or even Google, let's say that, think about like the data that Google holds about you and makes business on it, that suddenly gets available to everyone. So where Google is going to make a competitive advantage by just collecting data that others don't have. So you have this kind of an arms race in terms of collecting data. Again, positive feedback loop. Even more data will go in the wild. And then there's also, I'm very concerned with that, identification and attribution. Think about like the power of a proof in front of a judge, like a fingerprint. Oh, you are a person accused of having done something bad, whatever criminal things, and then you say no, I was not there. I'm not the person who has done that, but the judge says, yeah, but there's evidence, fingerprint, DNA, whatever. What can you do in order to justify the fact that you were not there? That's an issue, I think. In terms of safeguard of justice, it's super important. So I think I'm done. We can have so that's a much nicer cliff. There's no asset at risk. Thank you for your attention. I'm ready to take questions.